this today. 6 cards today. Let's start the clock. I'm pretty tired, but let's see what we can do here. So in this chapter, we'll start by talking about storage engines that are used in the kinds of databases that you're probably familiar with, traditional relational databases, and also most so-called NoSQL databases. We will examine two families: storage engines, log-structured storage engines, and page-oriented storage engines such as B-trees. Oh my god, I'm so fucking hungry. It's Also, I had an idea, just real quick. Um, so I forgot that iPads could be used as like external displays. I only have one display at the moment, and I'm wondering if I get an iPad, if it'll be more useful than just this. It would also be an external display. I guess there's not much to talk about. It would be useful. I could carry it with me. And I'm sure there's some attachment I could get for my laptop so that, like, if I'm traveling, I could also have two displays. Anyway. But okay, let's not get distracted here. Consider the world's simplest database implemented as two bash functions. So echo, bash stuff. Obviously, a getter and a setter. The getter greps a file probably called database. Yeah, and then it looks for the key and it sets the value. Okay. Yeah. So it can be almost anything you want. The value could be a JSON document. You can call dbget key, which looks up the most recent value associated with that particular key and returns it, and it works. The underlying storage format is very simple. A text file where each line contains a key value pair separated by a comma, roughly like a CSV file, ignoring escape issues. Every call to dbset appends to the end of the file. So if you can update a key several times, the old versions of the value are not overwritten. You need to look at the last occurrence of a key in a file to find the latest value. Hence the tail minus n1 in dbget. dbset 42. What? Oh. Cat database. Our dbset function actually has pretty good performance for getting something that is so simple because appending to a file is generally very efficient. dbset, I think I said dbget. Similarly to what dbset does, many databases internally use a log, which is an append-only data file. Real databases have more issues to deal with, such as concurrency control, reclaiming disk space so that the log doesn't grow forever, and handling errors and partially written records. But the basic principle is the same. Logs are incredibly useful, and we will encounter them several times in the rest of this book. In this book, log is used in the more general sense, an append-only sequence of records. It doesn't have to be human readable. It might be binary and intended only for other programs to read. An index is an additional structure that is derived from the primary data. Many databases allow you to add and remove indexes, and this doesn't affect the contents of the database, it only affects the performance of queries. Maintaining additional structures incurs overhead, especially on writes. For writes, it's hard to beat the performance of simply appending to a file. Because that's the simplest possible write operation, any kind of index usually slows down writes because the index also needs to be updated every time data is written. I knew that. This is an important trade-off in storage systems. Well-chosen indexes speed up read queries, but every index slows down writes. For this reason, databases don't usually index everything by default, but require you, the application developer, or database administrator, to choose indexes manually. Using your index of the application's typical query patterns, you can then choose the index that gives your application the greatest benefit without introducing more overhead than necessary. Okay, so I've written 0 notes down. Let's see, this introduced the concept of a log. Oh. So we should probably note that. Specifically our append the program's indexes or upfront Let's start with indexes for key value data. Uh, Key value stores are quite similar to the dictionary type that you can find in most programming languages, which is usually implemented as a hash map. Described in many algorithm textbooks. So we won't go into detail how they work here since we already have hash maps for our in-memory data structures. Why not use them to index our data on disk? Let's say our data storage consists only of appending to a file, as in the preceding example. Then the simplest possible indexing strategy is this. Keep an in-memory hash map where every key is mapped to a byte offset in the data file. The location at which the value can be found is illustrated. Key 1, 2, 3, 4, 5, 6, byte offset 0. Key 42 is at 64, yeah. When you want to look up the value, use the hash map to find the offset in the data file. Seek to that location and read the value. Storing a log of key value pairs in a CSV-like format, indexed with an in-memory hash map. That sounds like a terrible idea. So this may sound simplistic, but it is a viable approach. In fact, this is essentially what BitCask does. Offers high performance for you to write. Subject, oh man, I'm tired, to the requirement that all the keys fit in the available RAM. So that means if your computer shuts down or the program stops and it releases all of it, it's all gone. A storage engine like BitCask is well suited to situations where the value for each key is updated frequently. Got it? For example, the key might be the URL of a cat video, and the value might be the number of times it has been played. Compaction. We can then perform compaction on these segments. Compaction means throwing away duplicate keys in the log and keeping only the most recent update for each key. Okay. Oops. Moreover, since compaction often makes segments much smaller, assuming that a key is overwritten several times on average within one segment, we can also merge several segments together at the same time, performing the compaction Segments are never modified after they have been written, so the merged segment is written to a new file. The merging and compaction of segments can be done in a background thread, and while it is going on, we can still continue to serve read requests using the old segments file. That's cool. And write requests to the latest segment file. Okay. After the merging process is complete, we switch read requests to using the new merged segment instead of the old segments, and then the old segment file can be simply be deleted. Each segment now has its own in-memory hash table, mapping keys to file offsets. In order to find the value for a key, okay, compactions create segments. Segments can then be merged. By doing all this in the background, we can serve reads from the old files and serve writes to the new files. Once compaction and merging is complete, we delete the old files. Wait, what's this? We first check the most recent segment hash map. If the key is not present, we check the second most recent segment, and so on. The merging process keeps the number of segments small, so lookups don't need to check many hash maps. Lots of detail goes into making this simple idea work in practice. Briefly, some of the issues that are important in real implementation are file format. CSV is not the best format for a log. It's faster and simpler to use a binary format that first encodes the length of a string in bytes, followed by the raw string without need for escaping. If you want to delete a key and its associated value, you have to append a special deletion record to the data file, sometimes called a tombstone. When log segments are merged, the tombstone tells the merging process, I've learned this before, to discard any previous values for the deleted key. Crash recovery. If the database is restarted and in-memory hash maps are lost, in principle, you can restore each segment's hash map by reading the entire segment file from beginning to end and noting the offset of the most recent value for every key as you go along. However, that might take a long time if the segment files are large, which would make server restarts painful. By storing a snapshot of each segment's hash map on disk, which can then be loaded into memory more quickly. Nice. Partially written records. The database may crash at any time. Not if it's maintainable, scalable, and I forgot the other one. The database may crash at any time, including halfway through a pending record. To the log, bitcask files include checksums, allowing such corrupted... Okay, so I've never actually known how I've never actually known how checksums like work fundamentally. So I just asked ChatGPT from a larger set of data. Hello. You take your original data, you apply a checksum algorithm to it, like a hash function, but simpler. The algorithm produces a short result, the checksum. Later, when you or someone else wants to verify the data, you run the checksum algorithm again and compare the new checksum to the original one. If they match, the data is very likely intact. If they don't match, the data has been altered or corrupted. So for a database, I guess the first thing you would do is produce a checksum and append it to the file. As writes are appended to the log in a strictly sequential order, a common so an append-only log seems wasteful. Oh man, the fatigue is setting in right now. Oh. Oh, am I putting this all under hash indexes? Is that where I'm at right now? Oh yeah, this is all hash indexes. Oh, because we're talking about compaction emerging on the index. Got it. All right, let's finish reading this section. There's not much left. An append-only log seems wasteful at first glance. Why don't you update the file in place, overwriting the old values? But append-only design. So appending and segment merging are sequential write operations, which are generally much faster than random writes, especially on magnetic spinning disk hard drives. To some extent, sequential writes are also preferable on flash-based. We will discuss this issue from further in comparing B trees and LSM trees. Concurrency and crash recovery are simpler if segment files are append only or immutable. For example, you don't have to worry about the case where a crash happened while a value was being overwritten, leaving you with a file containing part of the old and part of the new values spliced together. Problematic. Merging old segments avoids the problem of data files getting fragmented over time. The hash table must fit in memory, so if you have a very large number of keys, you're out of luck. In principle, you could maintain a hash map on disk, but unfortunately, it's difficult to make an on-disk hash map perform well. It requires a lot of random access I/O. It's expensive to grow. Range queries are not efficient. So I actually don't know what's a data file fragmentation. I feel like I know that word, but Yeah, fragmentation. Okay. Cool. However, the hash table index also has its limitations. It has to fit in memory. And then range queries are not efficient. All right, let's come here. Throughput is given a workload, how much time it takes a system to handle a specific workload. So that's good. Social networks. Anything that has a lot of many-to-many relationships. Okay, so in a declarative query language like SQL means that we don't tell the system how to get what we want, we just describe what we want. The benefits of this are it's an abstraction, so you can optimize how you get it under the hood. A declarative language is when you say what you want but not how to get it. Good. What are the downsides of imperative queries embedded in application code? Tightly coupled with business logic, error prone, and less efficient. Harder to optimize, I'll take that. Okay. MapReduce is a programming paradigm where you ship snippets of code to be performed on each piece of data. Model for processing large amounts of data in bulk across many machines. Hard. Tombstones are special log records to indicate a record should be deleted. And compaction means merging segment files to remove duplicate rows from an append-only log. Or append-only index, I guess. Or log, I guess. Dang, I still have 5 minutes. Alright. Let's skim the next few pages, I guess. We won't take notes here, but just to set us up for next time. I wonder, could I ask ChatGPT this will be interesting. I asked it to provide an illustration of compaction. That's weird. Where does C come from? Huh. okay. I'm just staring at this. That's all right. We can stop here.